The picturesque lagoon on which the iconic city of Venice was built has always been this former maritime power's lifeline, offering crucial protection from the mainland and easy access to the sea. But the very waters that were its historical ally also became Venice's greatest enemy, with recurrent flooding across vast tracts of the city. In a marvel of modern naval engineering and heavy lift technology, the Italian government and a consortium of private enterprises is building a 7.3 billion euro water barrier system to safeguard this romantic city of water for future generations. The streets of Venice flood, a phenomenon known here as Acqua Alta, when strong southeasterly winds and a high astronomical tide cause an unusual inflow of water into the Venetian lagoon. Exceptional tides, measured here at Punta della Dogana, have occurred more frequently over the last century and risk catastrophically damaging the whole lagoon and the city itself. Venetians have long been accustomed to coping with the inconvenience of Acqua Alta. In 2003, the Italian government began building an ambitious feat of engineering to stop the devastating high tides and save the city. A massive surge barrier with 78 floating gates to close off the lagoon when flooding occurs.
Let's say it's a problem of preservation of the city's monumental heritage.
Thanks to exchanges with the environmentalists and to the improvement of the technologies, we have created the most important and probably the greatest environmental initiative in the world.
You can't just finish part of it and then see if it works. We're going to have to wait until it's completely finished.
Venice is sinking due to a twofold mix of natural and man-made problems. Climate change has caused the Adriatic to rise, but Venice also suffers from shifting plate tectonics, meaning the ground underneath the city is sinking. This problem is made worse by the reckless pumping of groundwater for use in petrochemical plants nearby.
We estimate that the sea level has risen by 12 to 13 centimeters, so the sum of rising sea levels and the sinking soil totals about 25 centimeters. So the city of Venice over the course of the last century has sunk approximately 25 centimeters with respect to the average sea level.
In 1966, flood levels in the city reached a record 1.94 meters, roughly 6 feet, causing immense damage to the city's building and giving birth to the Save Venice movement. Recognizing the need for a permanent solution, city authorities hatched a plan for the separation of the lagoon from the sea at high tide. The project was baptized Mose, an acronym that stands for Modulo Elettromeccanico Sperimentale, or Experimental Electromechanic Module.
In 1966, Venice flooded dramatically. It was the worst flood ever recorded and lasted longer than ever before. And so the Italian government decided that Venice had become a national problem and that the city had to be saved from the high waters. So, from that moment onwards, a series of ideas emerged, and then projects were launched that are now being concluded after many years, to create a system that stops the rising waters outside the Venetian lagoon, protecting the city from flooding.
The Mose project was all the more ambitious because of the geography of Venice. The Venetian lagoon was formed about 6,000 years ago as the coastal plain shifted following the last ice age. Today, it stretches 550 square kilometers from the river Sila in the north to the Brenta in the south. The city of Venice and the smaller islands around it altogether only account for 8% of the lagoon area, while 12% is permanently covered by open water and canals, and 80% is mudflats, tidal shallows, and salt marshes. In fact, it is one of the Mediterranean basin's largest wetlands. The lagoon is connected to the Adriatic Sea by 3 large openings in the natural sand barrier. They are the Lido, the Malamocco, and the Chioggia inlets, where the tide enters and exits twice a day.
The seawater enters the inlets and spreads gradually into the lagoon. From the inlets, it spreads along the canals. It goes faster along the canals, but also around the sandbanks and the deeper areas. And when the tide recedes, the sea level goes down, and the waters flow out of the lagoon inlets once again.
During and after the fall of the Western Roman Empire, the inhabitants of the Venetian coastal plain fled the invading barbarians and came to live on the dozens of islands surrounded by the shallow lagoon for the protection it afforded. Over the centuries, the lagoon became a natural base for the great Venetian trading empire. The Venetians built their city by driving giant oak poles up to 4 meters into the muddy flats, effectively petrifying and preserving them. They put planks on top of these pillars and marble foundations on top of the planks. Over time, the Brenta and Sila rivers deposited in the lagoon, blocking the navigation channels, and Venetians found it necessary to redirect the rivers so they flow directly into the sea instead of into the lagoon. Large-scale naval engineering projects, including hydraulic pumping and the redirection of rivers, have been underway for centuries and have altered the natural evolution of the lagoon, creating canals and a number of artificial islands. Battling high and low water has been a part of Venetian life for hundreds of years. The Mose project, however, is the most complex and massive naval engineering project in the city's history. The idea that Venice could be protected from the sea by a series of barriers began to gain traction in the 1970s. Other surge barriers in London, St. Petersburg, Russia, and Rotterdam in the Netherlands showed that the concept could work, but actually building it in Italy proved far more complicated than expected. Like all costly big engineering projects in Italy, it encountered strong opposition from environmentalists, became vulnerable to corruption, and fell into a web of contradictory local and national powers.
When the project was first designed 30 years ago, it was essentially an engineering project, and so we approached the problem in a very, let's say, hard way. Today, there are 2 sides to the project: the engineering side, but also the environmental side.
Construction of the Venetian Mose began in 2003, and the surge barrier is expected to be complete and fully functional in 2018. The Mose project was tailor-made to protect Venice, with 4 major barriers installed at the 3 main lagoon inlets that connect the lagoon to the Adriatic Sea. The Venice surge barrier consists of 78 floating steel floodgates arranged into 4 rows of various sizes, widths, and lengths. They are all independently operated and housed in tanks anchored to the sea floor. Each gate lies horizontally on the seabed when not in use, but when the tides over 110 centimeters are predicted, the barriers rise up on their hinges. After the threat passes, the air is released and the barriers can sink down again.
The flotation forces do most of the work. Think of them as buoys, which are submerged except for the last part. so they are controlled with pressurized air inside the barrier and absorb the force of the wave, but the air inside the barrier compensates for it.
Subiscono la forza dell'onda, cioè la spinta dell'onda, ma l'aria all'interno della paratoia la contrasta.
Over time, the Mose project morphed from being a purely engineering project to encompass also the recovery of lagoon wetlands that had been eroded over the centuries, and the recovery and restoration of Venice's ancient arsenal, which became the control center of the whole project, now run by the construction consortium Venezia Nuova, or New Venice.
The work we have done over the last few years has been varied. Land recovery, reinforcement of the coastline, decontamination, protection of polluted areas. All this to regenerate and improve the lagoon and the quality of its water.
Over the course of a 15-year infrastructure project, the work has often been bogged down by political quagmires and kickback scandals. One of the most vocal opponents of the Mose project is Luigi Lazzaro of Lega Ambiente.
This model, this Italian style of managing the bids and sub-bids in-house that determine who gets the project and then inflating the costs year after year is a direct result of the new public works law. Now we are up to 7 billion euros, with the Mose maybe being completed in 2016. Then we'll see how much money it will cost in the future.
It is one of the most complex and costly public works projects in Italian history.
The budget of the construction is approximately 5.5 billion euros, spent over 10 to 15 years for construction. In general terms, we think maintenance will be 30 to 40 million euros a year.
Noi pensiamo che la cosa sia fra i 30 e i 40 milioni di euro all'anno.
But it is the Mose surge barrier that is at the heart of this massive new effort to protect Venice. The heavy lift company Fagioli was called in to move some of the key elements of this massive engineering operation, together with construction company Mantovani, the Venice Water Authority, and the privately owned consortium Venezia Nuova. After centuries of devastating floods, a plan to save Venice from the rising sea and the sinking city finally surfaced. Each of the 12,000-ton concrete housings had to be moved from the building site to the lagoon entrance. While the Lido and Chioggia barrier housings were built close to their final destination site, the caissons for the Malamocco lagoon entrance were built far from where they were to be laid. Moving the concrete barrier housings from the building site to their designated place on the sea floor, and then installing the mobile barriers was an epic lifting job. Fagioli first had to deliver a lifting structure that would allow the caissons built for the Malamocco entrance to be lowered into the water, as the site could not be flooded like the others. In order to sink the caissons here, the consortium built the largest synchro lift in the world, made up of 26 beams, each 57 meters long, activated by hydraulic winches that could lower the caissons underwater so that they could, in turn, be lifted and transported.
The synchrolift is a synchronized elevator that allows us to lower things in water. Structures that aren't only very large in size, but above all, extremely heavy. And with this lift, we can carry caissons that weigh up to 22,000 metric tons.
The massive crossbeams of the synchrolift were transported onto a specially designed barge using self-propelled modular transporters. They are equipped with dozens of wheels that can rotate individually through 90 degrees in order to move massive weights in any direction. It took 3 to carry each of the beams to the barge, where they were loaded and taken to the construction site, where they were laid side by side and attached to the massive hydraulic jacks that provided the lifting and lowering power. Fagioli was also contracted to move some of the concrete caissons from the Lido Tre Porti building site. In order to move the massive concrete caissons, Fagioli engineers designed a unique tool for the job. They designed a catamaran structure with 2 river barges bound together with crossbeams equipped with strand jacks. A special wedge-shaped connection provided the catamaran with the necessary rigidity to perform the massive lift. The unit was designed and built at the Fagioli yards at Cremona on the Po River, under the direction of Loris Giovannini.
Il porto di Cremona è stato un polo molto importante per il Mose.
The port of Cremona has been a very important location for the Mose project in that it had the shipyard where the catamaran was pre-assembled. The catamaran was constructed out of 2 existing river barges that were taken out of the water in the port of Cremona, put in the dry dock in order to modify them and utilize them as the catamaran. In the port of Cremona, the 2 crosshead beams were constructed that would constitute the catamaran. Once assembled in the dry dock, the whole catamaran was disassembled and, piece by piece, barges and beams were transported to the Lido Tre Porti.
E pezzo dopo pezzo, mi riferisco a chiatte e travi, sono state poi portate al Lido Tre Porti.
For this heavy lift job, the catamaran needed a total of 20 strand jacks, able to lift from 45 to 294 tons. They do the heavy lifting of the concrete caissons.
In particolare sono stati utilizzati 4 strand jacks per la
4 strand jacks were used to sink the caissons. There were 4 vertical strand jacks that let us sink the caissons to their correct depth.
Dopodiché sono stati utilizzati 12 strand jacks.
Then we used the 12 L50 strand jacks with a capacity of 50 tons for the secondary mooring. That connected the caissons to the catamaran. Then, another 4 L300 strand jacks with a 300-ton capacity were used for the primary mooring system, which allowed the catamaran to move the caisson to its final resting place.
Fino alla posizione finale di installazione.
The single most employed instrument in all the transportation of the 12,000-ton caissons of this mega project was the strand jack, which uses an electrically activated hydraulic pulley to raise massive weights spread evenly among the dozens of cables lifting the load. Strand jacks were famously used to pull the 100,000 tons of the Costa Concordia over 12 hours from a 60-degree list to the vertical in the 2013 parbuckling operation. In July of 2012, one of the massive concrete caissons on which the individual floating barriers were to be attached was ready to be moved. Once ready, the basin was flooded and the caissons started floating, but then had to be partially sunk by pumping the air out of the tunnels built inside them. 2 tugboats dragged the caissons one at a time out of the basin to a sheltered area. Though the caissons were secure, every safety precaution was taken to make sure nothing went wrong. Special propylene axle lines were fixed to the special transport trailers parked along either side of the shoreline. They crawled along with the slowly moving caissons. The heaviest lift of Italian history had begun. Once the caissons had arrived at the sheltered bay, the tugboats were disconnected and the launching operation began. The 2 tugboats were hooked up to the catamaran. The launching operations involved connecting the lifting points of the caissons to the catamaran for the so-called secondary mooring system.
Il cassone è stato consegnato a Fagioli.
The caisson was delivered to Fagioli already floating. It had a dry weight of 12,500 tons. It was connected to the catamaran Alpha inside the basin and then connected to the mooring system.
Arrivato esattamente sopra la zona di installazione.
Once we reached the exact point of installation, the caisson was ballasted until it became very heavy. Then it was dropped down to the seafloor by the hydraulic pulleys, or strand jacks.
Dal pelo libero fino al fondale marino.
Once the structure had been connected, the catamaran was pushed by tugboats until it arrived over the underwater primary mooring system. Long wires called trench access lines showed the pathway or line to follow in order to get the concrete structure over the trench carved in the sea floor and reach the precise sinking point. Once in position, the caissons were ballasted and sunk using strand jacks positioned onto the catamaran. Water cushions previously positioned into the seabed were filled, gently taking the load of the caissons before they reached the bottom of the trench. The bags were then deflated, allowing the placement of the caissons in their final position. Engineers used precise 3D computer models to place the caissons with millimetric precision and slide one against the other to form a single watertight line. Even the smallest error could mean disaster for the Mose project. However, this was just the first stage in the massive move. Once the caissons were lowered, the floating barriers had to be attached. This was a massive feat of engineering. In 2003, the Italian government began investing billions into a project called Mose, a massive barrier to control the tides flowing in and out of Venice from the Adriatic Sea. Here at Lido Tre Porti, the Mose construction site rises out of the sea, a massive grey wall of concrete. But what is underwater and how does it work? 20 meters beneath the sea are a series of massive concrete caissons.
Every barrier has its 7 housing caissons and 21 gates and 2 service tunnels, one on each flank.
Workers who build and maintain these undersea tunnels take a lift to the bottom of the shaft. It is an imposing labyrinth of metal, concrete, and cable. There are 2 tunnels, one for transport and another a lateral service tunnel in which repairs can be carried out in a hurry if there is a leak. Watertight rooms along the side of the tunnel host the attachment mechanisms connected through the watertight female housings to the male part of the hinges on the outside of the caisson, round which the barriers move when compressed air is pumped into them. Each of the hinge rooms is flanked by a service chamber that allows a diver to enter the hinge room to carry out any emergency repairs if it is flooded. The watertight doors need to be checked regularly. They must be kept closed at all times. Each caisson was lowered and pulled against the next with millimetric precision, so as to make the whole length of the undersea tunnel completely watertight. The next phase in building the Mose is positioning the mobile barriers. Once again, the heavy lift company Fagioli was called into play. In this hangar in the Maghera port shipyard south of Venice, the massive yellow floodgate is finally ready to be moved. If you think moving a piano is hard, imagine this 210-ton steel box. The whole process of moving the barrier out to sea would take 3 full days. Fagioli uses a special heavy lift transport vehicle to slowly roll it out onto the awaiting barge. It is a tedious and dangerous process to move such a beast. Finally, at dusk, the barge transported it at a snail's pace, passing by San Marco after nightfall. a brief glimpse of the very city it is destined to protect. In order to do the final, most delicate phase of installation at daylight, the crew docks for the night. Dawn rises over Venice. The city of water slowly wakes, doing its daily business by boat. The barge with the great yellow gate heads out to sea to its final resting place.
Successivamente alla posa dei cassoni, dei 7 cassoni.
After we lowered the 7 caissons, Floodgate was also involved in the laying and installation of the floodgates. To do this, we utilized a scaffolding structure that was constructed of trellis towers and beams connected to the towers.
E travi colleganti le torri.
The tailor-made system included a 4-tower structure with 2 crosshead beams on top, each equipped with 4 strand jacks, necessary to lower this gigantic 210-ton barrier into the water. The support structure was called the fishing beam, as it would be used to hook the mobile barrier with 14 by 14 axle lines. The axle lines had to be perfectly constructed. When the structures were ready, a large barge equipped with 4 sets of gantries was maneuvered into position, and the tower legs, connected to a bottom frame, were joined to the 4 tower sections. This was a delicate stage. Every connection had to be precise to the millimeter. Workers monitored every parameter using radar, adjusting the cables and hydraulic pressure as needed.
La chiatta con a bordo la paratoia è stata trasportata fino a Bocca Lido Tre Porti.
The barge with the floodgates on board was transported to the Lido Tre Porti inlet, and there it was floated under the 4 strand jacks mounted on the launching legs. The weight of the lifted floodgate is almost 250 metric tons. The strand jacks allowed the floodgates to be lifted from the barge and lowered onto the caisson with millimetric precision.
Con una tolleranza anche qui millimetrica.
Once the caissons had been laid, the barges loaded with the barrier were moved directly under the launching structure, so the fishing beam could hook the barrier. After this, the area was cleared from the barge, and the barrier was lowered into the water using the strand jacks. Then the mobile barrier was freed from the support structure and fixed to the caisson. Any misstep could send the 200-ton gate to the bottom of the sea. Finally, the barge came back to load the launching gantry system and repeat the whole operation with the other 3 barriers. This will be done 78 times. This is the old arsenal, ground zero of the fight to save Venice from sinking. Once the former shipyard of the Republic of Venice, today it is reclaiming its place as the power center of the city. Here, in the main command and control station of the Mose project, engineer Hermes Redi is in charge of managing the Mose's reaction to the combination of high tides and adverse winds.
As we've said earlier, the floods are caused by a combination of several events. One is the normal tide. The other is the southeasterly wind, which pushes the water towards the upper Adriatic, and so against the lagoon. And lastly, there is a standing wave which contributes to rising waters.
He works hand in hand with the engineers and technicians of the City Tide Center to analyze the meteorological and tidal data coming into the control room. It is here where the crucial decision is made to close or open the 78 gates that make up the barrier.
The parameters of the screen that you see on the upper left are the monitors that give us the actual position of every barrier, its position and its state, should we need to activate them. The central part is dedicated to the weather forecast. All the other screens give us information about the lagoon surroundings, the Mediterranean, and the Adriatic Sea. All the data near our area that allows us to have a clear picture of the meteorological situation.
Alla nostra zona che ci permettono di avere chiara la posizione e la situazione meteorologica.
There are many parameters that determine exactly how many gates are opened, where and in what order.
Potremmo avere una marea normale.
We can see normal tides, high tides, very high tides, and we can react to each individual situation differently.
Il problema in maniera diversa.
Today, science and technology allow for the forecasting of when flooding will happen, but there is a deadline.
Siamo in grado di prevedere con giorni di anticipo la possibilità dell'arrivo dell'acqua alta e anche
We are able to predict several days in advance when a flood tide will occur and to forecast the tides quite accurately. But obviously, as we get closer to the day of the flood tide, our ability to forecast what will happen improves. So therefore, the real moment to decide whether or not to close the lagoon with the flood barriers happens about 3 hours before the event, because at that time, we can determine with total certainty what is about to happen.
Prima dell'avvenimento, perché in quel momento siamo in grado di prevedere con una precisione assoluta quello che capiterà.
Multiple meteorological factors must be calculated. The decision was made to use the Mose only when the tide is at 110 centimeters above average or higher. Under this scenario, flooding will still occur. Using various simulations, Venice authorities are able to determine with precision exactly what impact floodwaters of different levels will have on their city.
Venice is underwater in a very small number of places when the sea rises 80 centimeters above the average sea level. But the areas subject to this flooding, as you can see, are the most famous areas of the city. St. Mark's Square is the first to flood, and Rialto immediately afterwards.
But when the water level rises to 100 centimeters, 1 meter, above average, St. Mark's Square is completely underwater, and some smaller streets begin to have some problems. At 110 centimeters, the famous rubber boots become a necessity to get around the city.
At 130 centimeters, the city isn't completely flooded, but it is certainly completely impacted, which means that not only the ground floors and not only the shops are flooded, but the storerooms can't be used, and people can't get around freely.
At 140 centimeters, rubber boots are no longer any help, and the city becomes extremely difficult to navigate. But it is the epic flood levels like that of 1966 that are the biggest worry.
Basically, in that situation, Venice is completely underwater.
Once the Mose has been activated, the 78 single barriers emerge from the seabed in groups of 4, effectively creating a wall between the lagoon and the sea. A control system keeps the inclination of the gates when closed at approximately 45 degrees, constantly adjusting the water inside. When it is time to open the barrier, the gates are filled with water, a process called ballasting. They slowly come to rest flush with the seabed, invisible from above. Massive hinges that weigh 42 tons keep the gates attached to their bases. There are small gaps, just a few centimeters wide, which allow a little water through, but more importantly, allow the gates to move and rotate on their hinges as necessary. In October of 2013, the first test was conducted on the Mose, and the gates were raised ceremoniously out of the sea.
The precise data is boring, but I can tell you that just by closing half of the inlet, you could definitely see a lowering of the water level inside the lagoon. So the Mose works. The tide was slowed.
However, there is more to the Mose than simply massive engineering. Over the years, despite the scandals attached to it, the Mose has contributed to restoring other areas of the Venetian lagoon, But even those efforts are not without controversy. In an effort to preserve the uncontaminated natural environment, environmental groups often oppose big civil works like the Venetian Mose barriers. In this case, however, the ecosystem in question is far from natural. Sediments carried by the many inland rivers originated from the lagoon itself in ancient times by sinking and consolidating below sea level. For the Mose, new concrete walls and embankments were built, and even a brand new artificial island was created at the northernmost Lido inlet to host all the service buildings that control the barriers. On one side of the island is a lock system, a deep canal for tankers and cruise ships, and on the other side is a shallower canal leading north. However, not everyone agrees that the lagoon should be open to large ships at all. In Italy, there have already been disasters associated with large naval vessels. If one of these ships were to sink in the lagoon close to Venice, it would be catastrophic, both for the environment and the residents alike.
It has made the city slave to the passing of these gigantic ships, ships that could very possibly create a legitimate threat of accident. Accidents like the ones that have unfortunately happened in this country, like on the island of Giglio with the Costa Concordia and the port of Genoa, two extremely grave incidents that have created terrible damage.
If Mose is to be successful, it needs to be complemented by projects that will restore the lagoon's natural structure and build up its natural defenses.
The part of the project that concerns the lagoon is one of the most urgent aspects of the work because it is necessary for environmental restoration of the deteriorated areas of the lagoon, but also the shore. The moment in which the floodgates prevent the tidewaters from entering the lagoon from the sea will spread out back along the shore, and so we had to reinforce the shore for this reason.
Some of these measures include improving water quality by dredging the canals, which improves the water exchange in the inner lagoon areas, securing runoff from dumps and industrial areas, reinforcing the seawalls surrounding Venice's island and canal banks, and restoring thousands of kilometers of salt marshes. Polluted sediment was removed from canals, but where was it taken? There is concern, due to some of the corruption scandals surrounding the project, that the mud polluted by heavy metals may not have been properly disposed of. And what about the 49 kilometers of new beach? Where did it come from? And who will manage it?
There is a risk here, just like in other places, from the excavation that brings in soil from the southern part of the lagoon, which is obviously polluted, and has been since the 60s, by petrochemicals deposited in the seabed from the Marghera industrial area.
Another concern is the impact Mose closures might have on the lagoon water quality. It is the sea itself that is responsible for keeping the lagoon waters clean, since there is no sewage system and black water is released into the lagoon. Some worry that closing the lagoon more frequently could tip this delicate balance.
It's the job of the sea and the tides to clean out the lagoon. And they come into the lagoon and they leave the lagoon twice a day. Clean water comes in, picks up the waste, and takes it back out into the open sea.
Experts predict that sea levels could rise between 25 and 50 centimeters between now and the end of the century. At the same time, Venice is sinking 1 millimeter annually. The more frequent the floods, the more often Mose must be used.
The frequency of the flooding could increase significantly between now and the end of the century, so the need to close the Mose barrier could increase from the present 5 times a year to up to 100 or 150 times a year, or even 200 times. And closing the barrier so often could have an impact on the quality of the waters of the lagoon and the city itself.
University of Padua professors are proposing a companion solution to the Mose, an audacious plan to raise Venice by pumping water into a soil and rock layer beneath the city.
Our proposal is to raise the city by taking seawater and building wells 700 to 800 meters deep, and then pumping the water into the rocks at that depth. Venice will rise. We have calculated that over 10 years it could rise as much as 25 to 30 centimeters very gradually.
Critics say the Mose project may go down in history as little more than a concrete icon of corruption and waste if it's unable to protect Venice.
It doesn't give any guarantees to the city that it won't flood, because with a meter or a little over a meter of water washing up here in Piazza San Marco, the city already has problems. In truth, this won't stop.
Either way, Mose is here to stay. While Mose officials say corruption scandals were reprehensible, that does not change the fact that Mose is a naval engineering feat of incredible proportions.
The work, in my opinion, is of extraordinary seriousness and quality. You have to think that for the caissons that are 60 by 40 by 28 structures, we have tolerances of less than 1 centimeter. In the last year, we put down 18 of these caissons, one every 15 days, without erring by 1 second or 1 centimeter from our plan.
The Mose construction is permanent, together with all its accessory parts, and we'll have to live with it, even if it's unable to respond to climate change, which it seems is about to happen.
Siamo tutti in attesa di questo 2017, 2016, 17.
We're all waiting in anticipation. Could be 2016, 2017, 2018. Waiting for the moment when we'll know for sure if it really works, so we can test if the project will be able to keep a significant amount of the flooding out.
Il flooding della città durante le alte maree.
After it had been pushed back several times due to the ongoing public works investigation underway, the Consortium of New Venice has determined a new June 2018 date for completion of the Mose project.
The whole project is about 87% constructed. It's missing the last 3 rows of floodgates that they'll need to install by the end of 2015.
Although there is some uncertainty about how effectively Mose will protect the city of Venice, 7 billion euros have been spent, and the project is currently the best hope the city has of not being swallowed up by the very lagoon to which it owes its fame. Without doubt, the Mose project has been a marvel of engineering that has utilized the toughest machines and technologies that the maritime construction world has to offer. If it does work to save Venice from more frequent devastating floods, visitors from all over the world will still have the opportunity to admire this wondrous city of water for decades to come.